All right, so now we move on to lesson 7 of relations and functions, and it's nonlinear relations and their intercepts. So let's take a look at our two different parts here. Well, we have part A, which is going to be introduce mapping diagrams and ordered pairs that represent relations, review independent and dependent variables, and then determine linearity of an equation given table of values equation or maybe a graph. Now, Part B then will become determining the x and y intercepts, including where multiple exists for quadratics, which extends beyond just relations and functions dealing with linearity and now goes to different types of functions. Okay, part A, we deal with linear and non-linear relationships. Well, a relation can be described in 6 ways: words, table of values, a set of ordered pairs, a graph, mapping, which is going to be our new one here, and then an equation. So what we're going to do below is we're going to fill in the blanks according to the same problem in 6 different contexts according to the different ways to represent relations. So in the first one, we can use words. And so they say the cost of parking at a particular lot is $2. And if we park here once, then it would cost $2. If we park there twice, it's going to cost $4. If we park 5 times, it will cost $10. Okay, using a table of values to represent that data, well, 1 time parked was $2, 2 times was $4, and then 5 times was $10. And we could also represent this as an ordered pair. When it was $1, or when it was parked 1 time, it was $2. Parked 2 times, it was $4, and finally parked 5 times, it was $10. Now, we can take this and put this on the graph where we have our x and y. And if I plot the data that we had below, above, we can use our ordered pairs. So I can go to 1 and 2, which would put me here. I can go to 2 and 4, which would put me here. And then finally, I can go to 5 and 10, which puts me at the top of the graph here. Now, before we discuss discrete or continuous data, we're going to do a couple different variations here. Okay, well, we can also put this into a mapping diagram, and mapping means, what if I have some form of x value or some input and I get some y output here? Well, when we parked once, it was $2. When we parked twice, it was $4. And when we parked 5 times, it was $10. It's a unique input that gives us a unique output, or what we would call a one-to-one function. Okay, equation. An equation that represents this relation, well, we know that the change in cost every time was a change in 2. When we go from our first to our second to our third example, it was a change in 2 to here, and then we saw a very exponential increase here, but that was because we went from 2 times parked to 5. So what we could do is say that between each number of times parked, or from 1 to 2 and 2 to 3, it changes by 2. Thus, we know that the rate of change is actually 2. So cost is equal to 2 times the number of times parked. And then we would go back to our graph and we would say, okay, well, if we want the b value or the y-intercept, if I park 0 times, I should pay $0. So technically we could expand our table and say that our b or our y-intercept is equal to 0, and thus our equation would be equal to 2 times the n value in this case, or cost is equal to 2 times the number of times we parked. The independent variable in this case is, well, the independent variable is the one that's our input variable. It's how many times we park. So we say it's n, or the number of times parked. The dependent variable is the cost, because it depends on the number of times we decide to park at this given lot. The input values are, well, n, it's the number of times we park. And the output values are the cost in dollars. So yet again, just like we had discussed in previous lessons, the independent variable is tied to our input values, and our dependent variable is tied to our output values. Now, is the data discrete or continuous? I would say that this is discrete, because we're not going to park 1.1 times. We're not going to park 1.8 times, 2.1 times. So we realize that it's only 1 time park, 2 time park, 3 time park, and there's going to be a specific output for that. And then we say, is the relation linear? Yes, of course, this relation is linear from our diagram here. What we could do is just draw a line of best fit, and we could say that the slope is consistent between any of those 2 points, thus it is a linear relationship. All right, now determining if a linear relationship or a relationship in general is linear. Well, from the graph, we can determine if it's linear if the points form a straight line. That one should be pretty obvious. From a table of values or a set of ordered pairs mapping a relation with the slope that's the same between any 2 points, that's also what we would call linear, and we know that that represents collinear, or when we talk about collinear, it's saying that they have the same slope. From the equation must be able to be written in y equals mx plus b. So if the equation can be written as y equals mx plus b, and both x and y are degree 1, remember from our exponents unit, if x has an exponent of 1 and y has an exponent of 1, we know these are represented as a degree 1. And more specifically, I had something like x squared, or I should say more specifically this, y equals mx plus b. We know because these are both degree 1, this is a degree 1 polynomial to some degree, but more specifically a degree 1 equation. A degree 1 polynomial from our polynomials unit would be something like x plus 2, and we would know that we have a constant and something to a degree 1, so that would be a polynomial of degree 1. But in this unit, we just want to make sure that y and x are both degree 1, and if they are degree 1 and can be written in y equals mx plus b, we know this equation is a linear relationship. And then finally, from a word scenario, we know the rate of change must be constant. What is the rate of change? Well, we actually discussed this multiple times in class. If the rate of change is what's brought up, that represents our slope value. So we could actually fill this in here and say that is synonymous to our rate of change. All right, let's go through a couple examples. Determine whether each relation is linear, and where possible, write a linear equation for the graph. Well, right away on surface value, this one forms an S shape, and any S-shaped graph like that clearly isn't linear, so we say nonlinear. In number 2 here, we see that we have a vertical line. Well, vertical lines, remember, are represented by x equals. And what does x equal? Well, in this case, it's 1, 2. It is -2. So this is definitely linear. It has an undefined slope, so we can't define it in terms of y, so it must be x is equal to -2. We go to our third example, and we have a y-intercept at -5. We have an x-intercept at 1, 2, 3, 4, 5. This is 5 up here. Thus, when we look at our rise over run, we go up 5 units over 5 units, and we get a slope or an m value equal to 5 over 5, which is just simply equal to 1. Now, when we want to put this in an equation, we know this is linear, just based on its general shape. It must follow y equals mx plus b to be linear. Well, we know that y is equal to the slope value, which we found was 1, x, and then the y-intercept, which is the equivalent of b, that was our -5. So it should be 1x minus 5. And then finally, we look at our last example here. We have a parabola that is horizontally rotated or transformed. So when we look at this, we would say that this is definitely not linear here. So this one falls under the not linear. All right, let's look at example 3 here. So example 3 says, let's determine whether each relation is linear. And if it is linear, let's write an equation relating to the two variables. Okay, so in our first example here, or first part of our example, we have 3 points. And remember, if we have 3 points, in order to get the equation here, we're going to have to determine the slope and the y-intercept. First of all, if we want to do the slope, well, we can use collinearity. So m1 is equal to, well, we can do 8 minus 5, which is the change in y, over 0 minus -2, which is the change in x. This gives me 3 over 2. Now, I want to do the same thing with the middle variable, or the middle ordered pair and the bottom ordered pair, because I need to show that these slopes are the same. So now, my change in y is 11 minus 8 over my change in x, which is 2 minus 0. This gives me 3 over 2. Slopes are the same, so we know these points are collinear. And now, y equals mx plus b, where m is 3 over 2x plus b. We need the y-intercept. Nice thing is, we're actually given the y-intercept. When x equals 0, and then we have some 8 value here, or some value for y, this means we have a y-intercept. So our y-intercept, or our b value, is actually equal to 8, and we can fill this in. Y is equal to 3 over 2x plus 8, and that would be our equation there. Let's do the same thing with our second box here. We're going to determine the slope of these first two lines. So m1 is equal to the change in y, which is 3 minus 0, with negative 5 minus a negative 6 being the change of x. We get 3 over a positive 1 because the double negative becomes positive. Now we want to compare these 2 points. m2 is equal to the change in y, which is negative 5 minus 3, over 3 minus a negative 5. Just like the last example, double negative in the denominator, and this becomes equal to negative 8 over positive 8, which is equal to negative 1. Now, these aren't collinear because they do not share the same slope. These two values are not the same, and as soon as you see that these are not equal, it's not collinear, and thus this is nonlinear. All right, let's go down to our next example here. So now I'm going to do the same thing we've done before. m1 is equal to our change in y, which is 9 minus 4, over 3 minus 2. That gives me 5 over 1, which is just equal to 5. I'm going to take the second 2 points and go m2 is equal to the change in y, which is 16 minus 9, over 4 minus 3. That's equal to, well, 16 minus 9 should give me equal to 7. And this is over 4 minus 3, which is 1. Thus, it's equal to 7. These two slopes are not the same, therefore nonlinear. These points are not collinear, so it must be nonlinear. Okay, now in this example, well, it may be difficult to look at this and say, okay, well, what's the ordered pairs? So what I'm going to do is I'm going to reorganize it. 4 and negative 8, 3 and negative 6, and finally 1 and negative 2. I'm going to create their bubbles again. And then realize that our input is our left value here, and then our output is the one the arrow points to. So we have x and y. Now these are directly across from each other, and we know their ordered pairs are directly across from each other. We need to do our slope calculations. So we would say that m1 is equal to, well, negative 6 minus a negative 8 over 3 minus 4. That's equal to, the double negative becomes a positive, and so I get, for this numerator, 2 over negative 1, or negative 2. And then I want to do the slope calculation for the second 2. m2 is equal to negative 2 minus a negative 6, which is the change in y, over 1 minus 3, which is the change in x. Yet again, the double negative becomes a positive, and thus I get 4 over negative 2, which is equal to negative 2. I see that the slopes are the same. These slopes are equal to one another. And as soon as I see that those slopes are equal to one another, now I need to calculate the b value, or the y-intercept. Here's how I'm going to do that. I know that we have our slope, and in order to get the y-intercept, I can now sub in that I have y is equal to negative 2x plus b. I'm going to pick one of these points, and in this case, what I'm going to do is actually pick, let's say, 1 and negative 2. I'm going to take one of those ordered pairs and realize that represents an xy pairing of 1 and negative 2. This xy pairing can be plugged in for the equation as negative 2 is equal to negative 2 times 1 plus b. And thus, we should get negative 2 is equal to negative 2 plus b. If I add the 2 across on both sides, plus 2 and plus 2, therefore, I'm going to get 0 is equal to b. So finally, therefore, my equation is y is equal to negative 2x, and because b equals 0, I don't need it, and that's my final equation there. What a b value of 0 is essentially saying that it crosses through the origin as the y-intercept. All right, determine whether each is linear. Well, remember, just by the equation, the thing that tells us if it's linear or not is if it's a degree 1 for both x and y. As soon as we see that there is something other than a degree 1 for x and y, it is automatically nonlinear. So let's say we look at the first one here. Well, the degree on y and x is 1, therefore, yes, this is linear. We look at the next example, 1 and 1 on both those variables, this is also linear. But then in C, we see that there's a degree 2, that is not linear. Yet again, we see degree 1 for both of these, so that's linear. We see a 3 here, so that's definitely not linear. We go over to these ones here, they're both degree 1, this is linear. Degree 2 from the exponent, nonlinear. Degree 1, that is linear. And then finally, this one's a bit of a trick one, but we're going to draw it out. If I draw just a basic Cartesian plane, which I will do in black here, there we go, and I label my x and my y. When they say y equals 4 and they're talking about a graph that would represent this, what they're actually saying is that we have a horizontal line at y equals 4. If y equals 4, that's just talking about a consistent y value that extends out infinitely both left and right. Now, is this linear? Yes. And what is its slope? The slope of this line is actually just equal to 0. There is 0 change in y over some change in x, and 0 over a change in x would just give me a slope value equal to 0. So yes, this one's definitely linear, and it actually represents a horizontal line. All right, this is where you want to check your understanding. Make sure you're make sure you get your practice on this, especially with these. You want to be comfortable with saying, okay, if I have certain inputs to certain outputs, is it linear? Is it nonlinear? How can I identify it? And just looking at equations and making sure you're comfortable with saying, yes, this must be linear. No, that isn't linear. So definitely get your practice with the check your understanding here. For part B of our lesson, part B, we're going to actually look at a couple graphs here. We're going to look at graph 1, 2, and 3, and we're going to determine some patterns based on where it crosses the x-axis and where it crosses the y-axis. So determining intercepts for nonlinear relations. Well, our first graph is actually linear, and if we look at this, they say list the points which it crosses the x-axis. So I'm going to put a dot here and then say, well, it crosses the x-axis at, in that case, -3 and 0 for y. Graph 2 crosses the x-axis at -2 and 3. So as an ordered pair, we'd write -2, 0, and 3 and 0. And then lastly, graph 3 crosses the x-axis at what looks to be -4 and +4. So we should put as ordered pairs -4, 0, and 4 and 0. Now they ask us a question below. They say, what do all points in this above, or part A, have in common? Well, we should realize that all the y values are equal to 0. If we look at every single point there, the y values are 0. So the y values are 0. And when the y values are equal to 0, these are called our x-intercepts. All right, now let's do the same thing, but except for we're going to look for our y-intercepts, which I'll label in blue. So my y-intercept here is at 5 and 0. So when I write that as an ordered pair, we have to write our x first, which is 0 and 5. We then go to graph 2 and realize our y-intercept is up here at 6. So I'm going to write that as an ordered pair of 0 and 6. And then lastly, I have a y-intercept on our circle here and here, which is at ±4. So the ordered pair would then become 0 and -4 and 0 and +4. Now, what do all these points have in common in C? You should realize that we have zeros for all the for all the x values, I should say. All the x values have a 0 value, so the x values are 0. And what does it mean when we have the x values that are equal to 0? We've actually found our y-intercepts. Okay, let's use this knowledge in the below example here. Example 3, algebraically determine the x and y-intercepts for each of the equations. Okay, to determine the x-intercept, we have to set the y value equal to 0. So we're going to go x squared plus 0 squared is equal to 16. Therefore, x squared is equal to 16. And to undo a square root, I'm going to have to do square root of 16, and that's going to give me ±4. Okay, as an ordered pair, our x-intercepts are therefore 4 and 0 and -4 and 0. Because if we square root like that, we have to plus minus. Now, my y-intercepts. My y-intercepts are where x equals 0. So x squared plus our y squared is equal to 16. Y squared is equal to 16. And thus, if I square root both sides here, I'm going to get a y is equal to ±4. And thus, my y-intercepts are 0 and 4 and 0 and -4. All right, and now for part B, or part B of this example, we're going to do the exact same thing. X-intercepts or when we set the y value equal to 0. So 0 is equal to x cubed minus 8. I add the 8 across here, so I'll do that maybe in red here or blue. I add 8 to both sides. This is going to give me 8 is equal to x cubed. In order to undo a cube, I have to cube root. And the cube root of 8 is strictly equal to 2. The y-intercept, I'm going to do the opposite. I'm going to set x equal to 0. So we have y is equal to 0 cubed minus 8. 0 cubed is just 0, so that eliminates away. And I get y is equal to negative 8. And now if I wanted to write these both as ordered pairs, my x-intercept would be written as 2 and 0, and my y-intercept would be written as 0 and negative 8. Now, some questions may pop up of, well, how come when you square rooted it was a plus minus, when you cube root it was just the positive? Well, in the case of cube rooting, we need to realize that the cube root of negative 8 actually has a value, and it's equal to negative 2. However, if I look at square roots, I cannot get a square root of a negative 4. That does not exist. That's actually not a possibility, is to square 4. Whereas with cubing, we can cube a negative value. And so when I cube root this specific value, I get cube root of negative 8 is negative 2. And if I cube root 8, I get a positive 2. They're totally distinct ways of getting 2 and negative 2, versus when I square root, I can get a plus minus, because when I square both of these, and I could actually show this below, if I do the opposite operation of square rooting and I square a negative 4, it's equal to positive 16. And when I square a positive 4, it also equals to 16. Whereas if I cube root, or if I cube a number, let's say I go over here and I cube 2 now. So I go negative 2 cubed, this will equal to negative 8. If I cube, there we go. If I cube positive 2, it's equal to 8. And yet again, distinct terms. So plus minus for square rooting, individual values for cube rooting. All right, now it's time to check your understanding. Make sure you go through this, check your understanding, because you want to be very precise on how do I get my x-intercepts, how do I get my y-intercepts, what does it mean to get an x-intercept in terms of the y value, what does it mean to get a y-intercept in terms of what specific x value I need to use.